Welcome in, everyone. On this episode of Renewable Energy Reality Check, we continue to discuss the reciprocal world of closed-loop infrastructure systems, including advanced waste-to-energy systems, water recovery and filtration systems, as well as advanced industrial and agricultural production processes, along with a couple of cool surprises. We're moving toward a truly closed-loop architecture where every output is a potential input and waste is redefined as a high-value resource. Today, I'll share with you the key technological breakthroughs that are making this possible. Let's begin with farmland and rural sustainability advancement. The evolution of these waste-to-energy systems creates the next basic, fundamental, and foundational keys to global fuel sovereignty, creating new energy vectors. Now, with the utilization of agricultural residues such as corn stover, wheat straw, and forestry waste, enables the production of next-generation fuels. Through sophisticated thermochemical processes like high-pressure gasification, particularly with technologies such as high-temperature Winkler or HTW, we're able to convert these biomass feedstocks into syngas. This syngas, a meticulously controlled blend of hydrogen and carbon monoxide, serves as the molecular backbone for synthesizing sustainable aviation fuel, or SAF, and green hydrogen. These waste-to-fuel pathways are not merely incremental improvements, they're critical enablers for global decarbonization, especially as stringent blending mandates for SAF take effect this year, compelling the aviation sector to diversify away from finite fossil-based feedstocks. But the innovation extends beyond metals. We are now pioneering the recovery of phosphorus, potassium, and other essential micronutrients from bioash, the residue of biomass energy production. This allows us to effectively close the nutrient loop, returning vital minerals to our agricultural field, thereby reducing reliance on virgin phosphate rock mining and enhancing soil fertility. Simultaneously, the metallic fractions recovered from both IBA and bioash directly feed the burgeoning demand for copper and aluminum in the global electrification grid. The remaining 85% of the processed ash, after meticulous material separation, is transformed into high-quality mineral aggregates, ensuring that virtually every particle of our waste stream is repurposed for the construction of our future infrastructure, from roads to buildings. We are seeing the emergence of a different hybrid energy model, where waste-derived syngas is combined with green hydrogen from electrolysis, producing fuels that are not only carbon efficient, but also economically viable and scalable at an industrial level. This represents the new energy frontier, remastering agricultural and industrial waste, once considered a liability, into the high-energy molecules that will power our global transportation networks, supply chains, and industrial processes. The statistical brilliance of reciprocal use, closed-loop systems will extend deeply into our manufacturing and agricultural production, fostering an unprecedented era of industrial symbiosis. Looking further into the manufacturing sector, it's intelligent processing on the rise, where the industrial byproduct of one process becomes the vital feedstock for another. A prime example is the recovery of high-purity silica sand from fiberglass manufacturing waste, which is then directly integrated into advanced wastewater treatment systems. This circularity is further amplified by the widespread adoption of zero-liquid discharge systems. These sophisticated water management solutions, employing advanced membrane technologies like high-pressure reverse osmosis and nanofiltration, ensure that 100% of industrial and agricultural wastewater is recovered and reused. This means no liquid waste leaves the facility, eliminating pollution and providing total water independence. This modular, resilient approach is crucial for operational continuity, particularly in regions facing increasing water scarcity, and it underpins the sustainability of both factory floors and drought-resilient agricultural operations. Another critical and highly impactful advancement is the standardization of ash mining as a source of both industrial and agricultural wealth. When waste is processed through advanced WTE facilities, it leaves behind incinerator bottom ash, or IBA. Historically, this material was often destined for landfills. Today, however, using cutting-edge AI-powered robotic systems such as Zen Robotics' Heavy Picker, they are deploying computer vision and advanced sorting algorithms to extract valuable non-ferrous metals, including copper, aluminum, and zinc, directly from this ash, with over 95% precision. This is not merely recycling, it is a strategic recovery of critical raw materials. Furthermore, there are new approaches to critical resource recovery being revolutionized by physical AI across various industrial sectors. We are increasingly viewing materials like coal fly ash not as a pollutant, but as a domestic source for rare earth elements, REEs, and other heavy metals. Advanced pre-treatment methodologies, including mechanical grinding, alkali leaching, and even novel biological methods, are being deployed to efficiently extract these critical materials, bolstering national resource security. In the realm of traditional recycling, physical AI is transforming scrap metal processing. Companies like Sortera Technologies, which recently expanded their capacity in Tennessee, are utilizing patented AI and advanced sensor fusion to sort mixed aluminum scrap into specific, high-purity alloy grades with unprecedented accuracy. This capability is paramount because it enables the direct reuse of these high-spec aluminum alloys in domestic manufacturing, significantly reducing the energy-intensive process of primary smelting, drastically cutting carbon footprints, and making advanced aluminum recycling a central pillar of the U.S. supply chain for electrification components. As we strategically secure our terrestrial and industrial supply chains, we must also turn our attention to the ocean, which will not be a vast carbon sink, but rather a frontier for mineral sovereignty and energy advancement. On the climate front, ocean alkalinity enhancement, OAE, is emerging as a leading marine carbon dioxide removal strategy. By carefully adding naturally occurring alkaline substances to seawater, it accelerates the ocean's inherent ability to convert dissolved atmospheric CO2 into stable bicarbonate. This process effectively locks away carbon for millennia, offering a durable solution to atmospheric CO2 excess and simultaneously combating ocean acidification. Major commercial investments, such as the recent $31 million deal between Frontier and Planetary, underscore the growing market confidence in OAE as a scalable, market-ready climate solution for the 2026 to 2030 horizon. Concurrently, this is pioneering marine mineral recovery, often referred to as brine mining. Through groundbreaking initiatives like the European C4 Value Project, we are extracting strategic minerals. These include lithium, magnesium, boron, and gallium. These critical minerals are recovered directly from the concentrated brine streams produced by desalination plants. This innovative approach leverages advanced technologies such as 3D printed adsorption modules and ionic liquid solvent extraction to selectively recover trace metals from highly saline media. By transforming desalination plants into third sources of raw materials, it circumvents the significant environmental and geopolitical challenges associated with traditional terrestrial mining techniques. And this secures vital resources for the age of electrification. To wrap this episode, we'll be ending with this key knowledge. The convergence of AI-driven recycling, advanced waste-to-energy recovery, and reciprocal industrial and agricultural processes is fundamentally redefining our industrial landscape. By treating every waste stream as a reciprocal resource, we are achieving far more than just meeting sustainability goals. Whether that's agricultural residue for SAF, incinerator ash for critical metals and nutrients, or desalination brine for the strengthening of domestic supply chains, fostering resilience against geopolitical disruptions. Powering the economic ecosystem of America's reindustrialization will be the creation of high-skilled jobs and fostering STEM education to career pipelines. The technologies discussed today will provide you with an unparalleled toolkit for the future. Now, it is incumbent upon us to see these solutions through to scale, building a truly resilient and reliable future, one in which more effective, efficient advancements are applied intelligently to make for a better world. That's all for this episode of Renewable Energy Reality Check. Keep it electrified and be sure to join us here again for the next one.